We're going to use the definition of a limit to prove the squeeze theorem. Folks, this is how math goes. You get a definition, you're presented with a theorem, and then the statement is proved, probably using some definition or some previous result. Remember that the squeeze theorem said that if we have three functions f, g, and h, such that f is the smallest, h is the biggest, and g is between them on some interval containing a, and if as x approaches a, the limits of f and h are both equal to some number L, then the limit of the function in the middle as x approaches a is also equal to L. Now, because we have a limit of f and g as x approaches a that both equal L, we can say that for every epsilon greater than 0, there exists a delta 1 that's positive and a delta 2 that's positive, such that the absolute value of f of x minus L is less than epsilon if the absolute value of x minus a is positive and less than delta 1, and the absolute value of h of x minus L is less than epsilon if the absolute value of x minus a is positive and less than delta 2. Because f of x is less than or equal to g of x, which in turn is less than or equal to h of x, for every x near a, we can say that there exists a third delta, delta 3, that's positive, such that f of x is less than or equal to g of x, which is less than or equal to h of x. You just wrote that, I know, but I want to be able to say that that's true if x minus a in absolute value is positive and less than delta 3. Now, we're going to let just plain delta be the minimum of the three deltas we've looked at, delta 1, delta 2, and delta 3. And if it's the smallest, we can say that if the absolute value of x minus a is positive and less than delta, then we've got everything we need. In particular, we know for certain that absolute value of f of x minus L is less than epsilon, and the absolute value of h of x minus L is less than epsilon. Whoops. That means that f of x minus L is between negative epsilon and epsilon. Or if I add L to all three parts of this inequality, I can say that L minus epsilon is less than f of x minus L, which is less than L plus epsilon. And I can make a similar statement about h. Oh, whoops. I shouldn't have that minus L in the middle there. Okay, so I've got f of x between L minus epsilon and L plus epsilon, and I've got h of x between L minus epsilon and L plus epsilon. Now I'm going to do something that's a tiny bit sneaky. I'm going to take the L minus epsilon less than f of x, and I'm going to take the h of x less than L plus epsilon. I'm going to write down those pieces. So L minus epsilon is less than f of x, and h of x is less than L plus epsilon. Now, folks, on this interval that we're talking about, we know that f is less than g, which is less than h. As it turns out, I don't need f and h anymore. I have that L minus epsilon is less than g of x, which is less than L plus epsilon. Now, if I subtract L from all three parts, then I have g of x minus L is between negative epsilon and epsilon, which means that the absolute value of g of x minus L is less than epsilon whenever absolute value of x minus a is positive and less than delta, which means that the limit as x approaches a of g of x is equal to L which is what we were setting out to prove.